Okay, guys, follow along with me here. What we're going to do is we're going to be talking about relative dating today and trying to learn a little bit about how to figure out which rock layer came before which other rock layer. So this is kind of like a game of what comes first. There's a lot of logic involved here. It's kind of fun once you kind of get the hang of it. What you're going to do here, without a whole lot of prior knowledge, is to try and order all of the layers, all of the things that have occurred in here. Some of these aren't layers, like P as a whole, or it could be a river or a lake or something like that. It's definitely cut away here. In order from oldest to the youngest, with the oldest going on the bottom all the way up. Now, the reason I did it like this is because when you do these block diagrams like this, the oldest layer is typically where? On the bottom, right? So if the oldest layer is on the bottom, it's easiest almost always to work from the bottom up. So start down here rather than up here, right? There's some things you could figure out pretty quick by starting from the top, but if you start from the bottom, it's usually a lot easier than starting from the top. So ask yourself, what's the oldest thing that's happened here, and put it down here. It doesn't matter if you get these wrong. We're gonna go over the answers here in just a minute, but I'm gonna give you a little bit of time to work on them. There's some hints as to some of the things we talked about, and we'll talk about them again. Superposition, original horizontality, unconformities, cross-cutting relationships, all those things are happening in this diagram. So do the best you can, and we'll talk about it here in a second. So let's work through and see if we can figure out which one goes where. So we're gonna start at the bottom, oops, with the oldest thing here. It's a little hard to see some of these. Try and draw them in a little darker for you. There we go. This is layer A down here. A little easier to see. Turn a couple of lights down. So who can tell me what's gonna go first? Yeah, here in E. Anybody have something different than E? Anybody have something different than E? Maggie, do you have something different than E?
I thought H.
Nobody said A, huh? So John says E. E would be correct. So here's a good law here, a good relationship. H can't come before something it cuts through. So this is cross-cutting relationships. What this is actually showing you, do you see how G is actually right here? So this is G, just like that's G. L is here as well. Try and do that with that other pen that I had. So this is also L. You can match these up. This was G here. C, do you see where C is over here? C is right there. So that gives you some help. E is also over here. So looking at this thing, this is faulted. There was an earthquake here. This thing faulted. Either this slid down or this lifted up, or both. But it went like this because it used to be together. So that puts E as the very first thing down here to occur. Okay, after E, what happens next? G would be correct. Okay, if you didn't get these, try and write them down as you go so you can kind of glance at your work so you know. So we had E, then G. So we're just doing law of superposition now, right? Which just basically says that the one on top is younger than the one on the bottom. So going in that vein, what's after G? L. Okay, and then C. Cool. So that gets us all the way to there. Now what happens? H has to happen because it cuts through all these layers, but doesn't cut through M or D or any of this other stuff up here. So what was H? H has to happen, and H is that fault. That's that crack where the earth has actually shifted. Okay, so after the faulting happens, then what's going to happen next? Yep, then we're back to just law of superposition again here. M. Now I want to point one thing out here because you're going to see this again later on. Is there any missing rock here? Do you see how there has to be missing rock? Because these are all angled, okay, and the tops of them are gone. So this is an erosion layer right here. This is what we call an unconformity. So there's definitely an unconformity right here. Point this out for you. Right between these layers right here is an unconformity. So there's missing time here. How much is missing? Who knows? Could be a couple of days, probably more than a couple of days. Could be years, thousands of years, hundreds of years. There's definitely missing time here. This has been worn off. It's an angular unconformity. Rock is gone. Anytime rock is tipped and then there's flat rock on top, we're missing some. Okay, so we've got M, and then after M we're going to D, so we're just following law of superposition. And then next is J. J's a little hard to see. J's labeled way over here. That's J. Okay, what happens next? Now it gets confusing. Good job. Did everybody get that? Dang, that was really good. So we know A happens next, and there's a couple of reasons, okay? Some things that are going to help clue you in on this. These little dots right here that you'll see in these diagrams, what that is, if I can try and draw that in here, those little dots, those are contact metamorphism. Trying to give you some hints here so that when you go to look at a more complicated one, it's a little bit easier. Those little dots tell me that if this rock has been metamorphosed, what does that mean about A? What's A? What kind of rock is it? Sedimentary, igneous, or metamorphic? Igneous. So A is actually it's a pluton of igneous rock. So this is magma that melted its way into all these rocks. Now, how do we know that it happened before N, which is the important key point here? Do you see how it's completely flattened off here? So it's been worn away, and also we can see that there's no contact metamorphism on N. What if it just got to here and stopped? Well, that'd be kind of weird, wouldn't it? But also, there's no little dots up here that where N's been heated and cooked. So it's only cooked this rock around here. Now you can tell that it's also had to have come after these layers here, which is confusing. It had to come after those because not only does it cut through those, but it cuts through all these as well. Like whatever it cuts through has to be there before you cut through it. So cross-cutting relationships is super helpful. Okay, so that gets us up to A. After A, what do we have? Now it's easy again. N as in Nancy, and then K, and then B, and then F, and finally P, which is either some erosion or it could be a river or even a lake or something like that there where the ground has been cut away, but it definitely cuts down. It's another cross-cutting thing where it cuts down. Good, so those are some major features on these we're going to look at as we go along. So you can keep looking back at this to help you. These will help you, these little definitions here. And we're going to talk about this right now. And while we talk, there is a little quiz online. Okay, so we talked about some of this stuff before, but let's dive back in here and take a look at some deep time. Okay, today is all about relative dating. The quiz is on there. If you find the deep time lecture 1 quiz, this is the one that we're talking about. So let's look at some deep time here. This is, of course, the bottom of the Grand Canyon. Myself, that was some muddy water, isn't it? So let's take a look here. And understanding the depths of time that happened throughout Earth's history has been kind of a big development for humans. Like, for us to understand that the Earth is so much older than we ever thought it was, it's really forever altered our perception of that. It's our perception of nature, even of the universe, right? And as Hutton said here, we find no vestige of a beginning, no prospect of an end. We do know that there's a beginning, but it certainly is much deeper in time than we ever thought it was. He said that in 1788. So what is deep time? And you can use this to help you answer that first question there. Just type off a little brief answer there. What we're talking about is just really the immensity of geological time, just how vast it actually is. it's hard for humans to grasp. I mean, I don't know about you, but I can grasp things in terms of years, tens of years, hundreds of years. When we start getting up into thousands of years, I start to have a little bit of trouble. But when we jump to millions of years, like, my mind starts to bulk. And then you add on top of that the concept of billions of years, like 4.5 billion years of history on our planet. That's a long time. And as a human, like, honestly, I can talk about it, but really comprehending it is difficult, right? We're used to, at most, dealing with units of maybe 1,000 years, if we're talking in terms of humans. But our geological time scale, it really deals in millions and billions of years. And you guys are going to be making some timelines in here. And we're going to set up our timelines so that 1,000,000 years equals a millimeter. Think about that. Yeah, right? In order to fit this thing on a piece of paper, we're going to make 1,000,000 years 1 millimeter in size. So Earth's history is vast. And we're not even talking about the history of the universe, just our planet itself and the sun and the other planets that are going around it. If we consider the Earth's history as the old measure of the English yard, which was actually the distance from the king's nose to the tip of his outstretched hand. How about that? Did you know that? So I don't know, did they change that every time there was a new king? Like, have to adjust measurements, guys. Suddenly you just lost some land, or you're going to gain some land because the king's got a shorter arm or a longer arm, right? But that was the original measurement, was from the tip of the nose to the outstretched fingertips. The longest finger was actually considered to be a yard. So one stroke of a nail file on that king's middle finger would erase all of human history. If we laid out the entire Earth's history as a yard and just took a nail file and went, beep, humans are gone. Right? To think about, like, how long we've been around compared to the depths of time, it's hardly even comparable, right? Okay, we already mentioned this stuff before. We talked a little bit about uniformitarianism, which is a heck of a mouthful. Everybody answer that question okay on the last one? Okay, cool. And this, of course, was put forth by James Hutton. And he said his famous phrase was, "The present is the key to the past," and we talked about that before. But it's just the idea that if we want to know how things are working in the ancient past, we need to kind of look at them today. In comparison, like these cracks that are happening in this muddy floor here, compared to these fossilized or lithified cracks that are the same thing, we kind of understand how they form because we can see them forming today, right? So that helps us understand it. But we also have to accept that geological change is pretty slow for the most part. It can take a long time for these mud cracks to form into rock. So let's go through these again. We talked about these at the beginning of the year, and let's kind of roll through them again because you're going to use them a whole bunch here for the next couple of days. The first relative dating technique is called original horizontality. So let's say this about relative dating before we get any farther. When we're relative dating, we're not affixing an actual exact date to anything. There's no exact date getting put on anything. All we're saying is this is relative to that. So relative dating has zero to do with dating your relatives. It's got nothing to do with that at all, yeah. That would be real awkward if we were talking about that in here. It has everything to do with saying this layer is older than that one but younger than this one. Notice I didn't say this layer is 4 point whatever billion years, this layer is 6.2 million years, right? I just said that one's older than this one. That's really all relative dating is. It's still really important. So the first concept, two concepts which really go together, is that of original horizontality, which tells us that layers of sedimentary rocks, because they settle, gravity makes them horizontal to Earth's surface. So if you find rocks that are not horizontal, that are sedimentary rocks, something's tilted them, right? And it's a whole bunch of layers of sedimentary rocks there in the Grand Canyon where I'm sitting, layer after layer of sandstone. I think it's actually all sandstone right there. Probably an ancient beach, right? The law of superposition just tells us that where rocks are originally undisturbed or flat like that, the oldest one is on the bottom, right? Super easy stuff. You guys can understand that. Okay. Let's talk cross-cutting relationships. You just use this one. It's probably one of the most useful tools in interpreting these diagrams. And that tells us that younger features have to cut across older features. If something cuts across something else, the thing it cuts through has got to be there first. And it's as simple as saying if I rip a piece of paper, the paper's got to be there before I rip it. It's really easy to screw that one up, but if you think about it, think it through, the neck of this volcano has to melt its way through rock that's already there. So the volcanic rock in that neck of that thing, in that dike, is younger than anything it cut through. It's the same thing about a fault. If there's a crack and the earth shifted, the crack has to be younger than whatever it cuts across. All right. Let's talk inclusions. We mentioned these before. If you find a rock that was some country rock, and it's included in some other material, the rock that got included has to be older. The inclusion is older than what's surrounding it. So this is going to help us out on some of these diagrams that we look at. And I've got two different situations down here on the bottom. The first one is you've got a sill, which is some igneous rock that melted its way between two layers of rock here. Okay. And I know that it melted its way. It's younger than this rock it's above here, that's above it, because that yellow rock is included in it. Okay, so that yellow rock fell off inside of it. So that yellow rock had to be there first. Okay, if I look over here to the picture on the right, there's another flow here. Notice how the pieces of gray rock, which were the inclusions in the yellow stuff, so totally different scenario, they have to be older than the rock that they're in. So this scenario here, this flow here, the top of it wore away and some of it got eroded. And so there's little pebbles on the surface and they got included in the sand that buried it on top. Do you see the two scenarios? The rule holds true in both pictures, but both pictures are the reverse of each other. No matter what, if you look at it and go, the inclusion, the little rock, has to be older than what's inside of it or what's holding it. So same thing on the left, same thing on the right. Kind of makes sense? But there's different ways you can have that happen. You could have liquid rock and rock fall into it, or you could have rock harden and then little bits of it get broken off and more rock get put on top of it. Right, so there's two different scenarios, but if you just remember the rule that the inclusion is older than what encloses it, the rest is easy. Cool? Okay, I don't want to go too fast here. Make sure I'm not zipping along here. We did superposition. We did horizontality. Everybody good on those? Cross-cutting relationships, we did that. We did inclusions. Nice. Okay. Everybody able to answer the inclusion question? It's probably the harder one on there. You just have to think about it a little bit. All right. Let's talk about baked contacts. We just mentioned these. This is some contact metamorphism. So what happened is igneous rock got intruded there. That's the intrusion on the picture. It pushed its way between other rock, and the rock above it and below it got baked. Now, if this is limestone, which it had to be, then the igneous intrusion baked the limestone into marble. So now you have this beautiful white layer of rock above and below where the igneous rock heated it. And there's the same picture, kind of similar down below. There's a plutonic igneous rock there, so this big bunch of magma down there bakes all the country rock around it, and so you're going to get different metamorphic rocks all around the edges. So that tells me kind of how far that thing pushed up in. So the rule is the baked rock has got to be older than what intrudes. And the cross-cutting relationships work too, because the pluton's cutting across layer after layer after layer. We know that it has to be younger than what it cuts across. And the rock that's baked has to be older than the pluton. Ooh, I just said a lot of words there. Now, what about that yellow layer on top? We don't know, do we? Was it there already, or did it get put down afterwards? So sometimes in some of these scenarios, there will be multiple answers that could be correct, because we maybe don't know. But we can say for sure about the relationships of all those other rocks. We just can't say for sure about that yellow one on top there in this diagram right there. Okay. All right, so let's talk unconformities. We mentioned these already. All an unconformity is is a gap in the rock record. And there's lots of ways you can get these. There's three main types. Okay, we mentioned some already. The first one over here on the left is called a disconformity. So here's a situation where you've got, and you don't have to remember these at all because all you have to remember is how to recognize them. And usually they're designated by kind of a wavy line. If you look there where it says disconformity between the Jurassic and the Devonian on the left in picture 3, there's this little wavy line right there. That wavy line is how we denote there's some missing rock. Some's been eroded away or some missing. So in a disconformity, we had water there. It deposited layer after layer after layer. The earth rose or the sea level fell. Either way, when there was no water, stuff started eroding away. So now we're missing some of that Devonian rock there. And then later, water inundates again, and we put a new layer down. So there's a gap there, and we know it. Here's a nonconformity in the middle picture. In a nonconformity, if we've eroded all the way down to the basement rock, which is igneous and metamorphic, we can assume that whatever's on top of it didn't come right next. There's missing rock above it because it's igneous rock or metamorphic rock. That's a little confusing. There will be a little wavy line if that's the case in a diagram. On the far right, anytime you've got angled rocks, angular unconformity, and you've got flat rocks on top of angled rocks, obviously you wore some rocks away. Doesn't work otherwise, right? So that can be really helpful for figuring out the order of these things. Let's do a trial here. Let's see here. Okay. Let's try this out. Can you guys kind of sort out how this sort of works here? A lot of complicated stuff going on, isn't there? So we've got some folded rocks. We've got some rocks in the bottom there. If we're looking at cross-cutting, those things have to be younger than the other things. So trying to sort this out, we might say, okay, the limestone there at the bottom had to have come first. And then it looks like a layer of shale, layer of sandstone, layer of shale, layer of, then there's a sill in there. But the sill has inclusions from both the shale and the sandstone on top. So it didn't come until later. So that next layer would have been the sandstone. See that? Then the sill intrudes into that because everything else cuts across that sill. Whew, see how complex this could get? Then the next thing that has to happen is that we've got to have some folding. The folding is going to happen next. So the whole thing got folded and bent like that. Then, see if I can keep going here. It looks like the granite pluton would have come next. Okay, because the fault cuts through the pluton and through everything else. So the fault would have been the next thing. And then the very last thing to occur would have been that basalt dike because it cuts through everything else. I think I did that right. That was just off the cuff there, but let's give it a shot here. I think I put all the layers on here. So there's 2, 3, 4, 5 is going to be that sandstone. 6 is going to, oh, I missed that one, didn't I? I forgot that one when I was explaining it. 7 would be the sill, because we've got the inclusions in it from both top and bottom. Okay. Then the folding occurs, and then the pluton cuts through everything. Then the fault happens, and then the basalt dike. So that's laying the whole thing out for you right there. Did that seem hard? Was that easy? There's a little bit of logic involved. Oh, and I guess erosion. We could throw erosion on there too. Spend some erosion up top. Okay, let's talk about one last thing here in relative dating, and that's fossil succession. So the last piece of the puzzle that helps us determine what happened first and when it happened is fossils. Since fossils only live for a brief amount of time before they either go extinct or evolve into something completely different, we can place things in time with fossils. And if you can find the right fossil, like for instance an ammonite, those things are really good index fossils because they lived throughout a long time geologically, and they changed very rapidly. So each individual species only existed briefly in geological time. So if you find it, they're easy to identify, and then boom, you can pick it out exactly what age the rock is if you've got no other information about it at all. And you can see kind of how those go. Some of them overlap, some of them don't. But because fossils succeed one after another, we can use them to order things. Okay, but it's helpful if they change a lot or go extinct, like exist briefly. We can help order things out really well. We're going to do some of that a little bit later. Okay, everybody have the relative dating one sorted out? You can hit complete on your test and your quiz. Okay, we're going to jump around in here a little bit. The first thing that we're going to work on today, and it's going to take us a few days to get through some of this, is we are going to jump over to let's do this page first, because I think it will be the easiest for you. Okay, we just did one of these. This is really similar to a quiz that you're going to get later on when we finish all this up. So you can hold on to this whole packet because we're going to use it for a quiz. Go through and use your knowledge again. Start with the oldest event, work your way up to the most recent here. And then I've got a couple of questions for you. Like, which one represents a fault? Which one represents intrusive igneous rock? Which one represents a place where erosion is currently happening? Okay. Between which two unexposed layers? Unexposed means they're not exposed at the top. Okay. Is there an unconformity? In other words, where is there definitely rock missing between which two layers? Okay. You're going to have to do some work. You have to figure out how these line up here, because there's been some faulting going on. It's a little tricky. Once you finish that, I'm going to kind of show you the rest of this package here so we don't have to do it later, because we'll work on it probably a little bit the next day too. The next thing we're going to be doing is cutting out these little squares right here. So this page and this page are all together as one thing, okay? And it starts out just from the bottom up again. There's 18 of these. This is number 1 at the bottom, and number 18 is at the top. So you're going to try and put them together and make a flip book. So it should flip through all the layers when you get done. So that'll be the next step. And I think that's probably as far as we're going to get today. If you get further than that today and want to play around, there's a little piece of extra credit here. I'll explain it right now. You can work on it a little bit in class, in and out of things. This is a road cut right here, and it is a really confusing mess. This is not an easy one. As you can see, what you need to do for extra credit is to color all of these. Like the granite has these little pluses in it. I would color it a color. And then I'm going to color, like I can see it right here. Okay. Be careful though. For instance, like the, let's see here. Where is the, there it is. The Muscovite hornfell right here. There's some of it here. There's some of it, little piece, you gotta look really close here. A little bit of it right here. Okay, you can sort it out if you're really careful. You'll figure out where things are at, okay? But this is a heck of a thing to put back together. And then what you're gonna do is you're gonna number it. So off to the sides here, like let's say I think that the granite is number 1, I'd put a number 1 there. Okay, like that's the bottom. And let's say like, maybe I think the olivine basalt is number 2, I'd put a 2 there. Okay, and some of these, the colors didn't show, so I'm going to do a little coloring on this to show you where they're at, to make it a little bit easier. But you're going to color them in and write the numbers. This is for extra credit if you want. And I'll tell you this much, there's at least a couple of these, maybe 2, where you could have them interchanged and you could still have the right answer. But it's tough. You have to work through it a couple times to figure it out. Okay, let's work on that next part. Okay, on the extra credit, I gave you a couple of hints here. So the olivine basalt is this dike right here that cuts up here. I colored that for you. You can color whatever colors you want, but this is just to show you where it's at on the diagram, since that didn't show up. And the quartzite, which is this folded stuff here, is over here. I colored it yellow. You color it whichever color you want. There's a little piece of it in there. This piece in here. Okay, this here, here, and here. That's all part of the same layer of rock. It's just been folded, okay? The other ones I think you can tell based on the symbols there. Just color these in. You don't have to color the basalt. It's already pretty dark it is what it is. It's right there. Okay. Okay, so when you finish sticking all these together, you should be able to actually create a little flip book, and it should work as you flip through it. And you'll see the layers going through. You can kind of see here as we go through. You see a volcano form, volcano get buried, some uplift, some folding, some more erosion. Trying to make this thing flip. Yeah, it's a little hard to do. There you go. Now, one last thing on the extra credit here. Tried to give you a little bit of help on this. If you're interested in turning this in, you don't have to do it. A couple of the rocks are hard to tell because they were both white. The quartzite is folded, and you see some here and here, here and here and here and here. And then the olivine basalt is here. Okay, the rest of the activities are for you to work through. And then there's going to be a quiz online about this. All right, once you finish that up, we have one last activity here before we actually do the quiz. So this is the index fossil activity, and there's kind of two parts to this. It starts right here. There's two sections. One is some cards that you're putting in order, and the other one is some index fossils. So it's really a similar situation. I don't care if you fill out the questions or not, because they're pretty obvious once you get this sorted out. But what we're going to try and do, this is another cut and paste one. Not paste, I guess, so much as cut. So here's some layers. You'll tear this out, and you've got, you can cut these again if you just want to try and order them. It's easier to see if you try and layer them up. The oldest layer is going to go at the bottom, right? So you're going to put TC on the bottom. Now both T and C are fossils, and T and C are found in the same layer. So how will you know what comes above it? Something's going to have to contain one of these two fossils, right? So this one's got a C in it. Are there any that have a T in them? No, so this one has a C in it. So C is a fossil that lived on into the next layer. So this layer would go above this one. Some of them are going to be more confusing. The only thing you really have to keep in mind is that a fossil can never go extinct and then reappear. It could live through multiple layers of rock, but it can't go extinct and then come back. So see if you can sort that out. The other page is exactly the same thing, only with actual pictures of fossils. Okay, so we've got eurypterids here, graptolites, brachiopods, trilobites, horn corals, plechipods, some shark's teeth. Okay, and I put oldest layers right here, so you know this one starts on the bottom, and then try and build your way above it from the bottom up. Remember, once a trilobite goes extinct, it can't come back. Okay, some things are going to live through multiple layers, though. See if you guys can sort that out, and then you can take the quiz online. There's one activity in here that we're going to save for later, so hold on to your packets. And that activity is this one right. This one right here about radiometric dating, we're going to be doing on a different day, so don't worry about doing this one. But we've pretty much completed everything else, minus the extra credit in there. And you don't have to turn these in. You're just going to do a quiz online with them. Okay?